My pleasure to introduce Liliam César de Castro Medeiros, coming from the University of São Paulo. She will talk about individual based model applied to epidemiology.
Good afternoon. It's okay. So I will present two models based on dengue fever. Okay. Thank you, Nicholas, to introduce the dengue and Wolbachia. So dengue is a viral disease transmitted in Brazil mainly by the Aedes aegypti mosquito, and there are 4 distinct serotypes of virus. And in Brazil, we have the 4 serotypes circulating, and the mosquito Aedes aegypti in all states of Brazil. Dengue fever is hard to control because of the many factors that influences the disease. Climate factors, factors related to human behavior, and factors related to the serotypes and the reactions of humans. And here I will present you 2 experiments, agent-based models, to analyze 2 control strategies of dengue, virtual models. And the first one, agent-based model to analyze the efficiency of dengue control strategy via the introduction of Wolbachia bacteria in Aedes aegypti mosquitoes. Wolbachia bacterium, it's a naturally occurring bacteria in 60% of insect species, includes some mosquitoes. It can only be transmitted from mother to child, but is not found naturally in Aedes aegypti mosquitoes. And the Wolbachia is able to block transmission of dengue virus in Aedes aegypti mosquito. So it's a feature of this bacterium, the cytoplasmatic incompatibility. So we will work with this infected male. When we infected the male copulates with an uninfected female, we haven't children. So in this model, we sought to analyze 3 issues. What is the minimum number of vectors infected with Wolbachia that should be released in a region to eliminate or minimize the number of vectors infected with dengue virus? What is the best spatial distribution of this release? And how often should the release be performed? So we created an agent-based model to represent the dynamic of dengue fever between humans and mosquitoes, and this model was based on this work. And we simulated the application of this control strategy with the introduction with mosquitoes infected with Wolbachia. So in the model represents a neighborhood. Each cell represents a lot with humans and mosquitoes. So our agents considered were the humans, the mosquitoes, and the immature stage of mosquitoes, but to simplify the model, we consider represented all in a single class. And the mosquitoes can be infected with Wolbachia bacteria, they can be infected with dengue viruses, or they can be free of both. To simulate, we used the NetLog environment. It's a multi-agent programmable modeling environment. And our virtual environment, we consider 2 types of lots, residential and public location. People goes more to public locations than to residential lots. And one consideration of the model is the human daily mobility. We consider that every day, the mobility is random, but every day, 70% of the people going to public locations and 30% of people go to residential areas. And with relation with mosquitoes' daily mobility, we considered that adult females in egg phase maturation or adult males, they have 10% of chances for moving to another nearby cell. And the case, the adult females that aren't in egg phase maturation, they move to a neighboring cell in which there is an adult male. And if there isn't the male to copulate, so it has a chance of, again, of 10% to move to another neighboring cell to meet a male. And the life cycle, based on these informations, from this Souza, the sum of immature phase of the mosquitoes, we considered the sum during 13 days, and the adult phase in average 30 days. But in the model, we consider that death rate, different death rates from these different stages. And in dengue stages, we consider the SEIR model to humans and SEI model to mosquitoes. And we considered the cytoplasmatic incompatibility. And with relation to copulation, fertilization, and egg posture, we considered the female can only copulate after 2 days of adulthood. It was based on literature. Every female mosquito of a suitable age is checked every day, and the female will be fertilized if there is an adult male mosquito within 1.5 cell of distance. And it's considered that a single copula is enough to fertilize all the eggs of the female. And these were the initial conditions of the model for all simulations, except these 3 conditions, because they are the parameters that we will change in the simulations. So the initial number of Wolbachia infected mosquitoes, number of releases of Wolbachia infected mosquitoes, and frequency of release of Wolbachia infected mosquitoes. And the simulation scenarios, we consider with relation to number of focus, number of Wolbachia infected mosquitoes, and number of foci. Initial outbreaks with Wolbachia infected mosquitoes, 1 outbreak or 2 outbreaks or 4 outbreaks in the space. And we considered that in the initial condition, we have 20% of the total mosquitoes infected with Wolbachia. And after the analysis of the best release distribution of Wolbachia infected mosquitoes, the following hypotheses of release were tested. Release in each 1 week, or in each 2 weeks, or in each 4 weeks. So, results. With relation to distribution of foci with mosquitoes infected with Wolbachia, the simulations with 1 and 2 outbreaks of Wolbachia infected mosquitoes presented less favorable results to control of the mosquito population infected with dengue virus when compared with the scenario with 4 release outbreaks at the same time. Here I will show you this. This one is the percentage of mosquitoes infected with Wolbachia, and this one is the percentage of mosquitoes infected with dengue virus. So we can see, and the initial condition was 4 outbreaks of Wolbachia infected mosquitoes. And the simulation showed the same qualitative patterns. So I show you one of them. And here we can see that at some time, the mosquitoes, it was only one release in the beginning of the model. So in one moment, we have that the mosquitoes infected with dengue virus increases and become larger than the amount of mosquitoes infected with Wolbachia. And with relation to release frequency of Wolbachia infected mosquitoes, different release frequencies were tested, only for the case with 4 outbreaks. So we begin with 4 outbreaks, and we will change the release frequency of Wolbachia infected mosquitoes. So we considered, it was observed that the amount of mosquitoes used in the preliminary release was not sufficient, and the foci rapidly dissipated. So we doubled the initial number of Wolbachia. In each release, the number of Wolbachia infected mosquitoes. And the simulation considering the release frequency of 14 and 21 days presented unsatisfactory results in relation to the control of mosquitoes infected with dengue virus. And the more satisfactory is the 7-day release frequency. So I will show you the graph generated when we consider the release frequency about 7 days for each release. So we can see the amount of mosquitoes infected with Wolbachia is larger than the amount of the mosquito infected with dengue virus in the model. So it's an initial experiment we made. We will make more experiments. In simulations, in some moment, the population of mosquitoes infected by the dengue virus exceeded the population infected with Wolbachia, requiring a longer time to change this. In the case of 4 outbreaks of Wolbachia infected the mosquitoes, and the number of humans infected by dengue virus during the simulation using 4 outbreaks of Wolbachia infected mosquitoes was lower in comparison to the other cases. And with relation to release frequency of Wolbachia infected mosquitoes, the frequency of 14-21 was insufficient to control the dengue, but the frequency of 7 days presented more satisfactory results, maintaining the mosquito population with dengue virus percentage close to 6% in relation to total mosquito during the simulations. We saw in the model the need for a minimum amount of mosquitoes per focus of release was observed to guarantee the maintenance of Wolbachia infected mosquitoes population. The frequency releases has been shown to be a critical and determinant factor for the control of dengue through this method, but other simulation configurations need to be tested because it was the first experiment. And the second model we made was to test the control strategy of via introduction of overtraps in the environment. The overtraps method consists of the spatial and periodic distribution of the overtraps in area to enable egg elimination. Eggs from Aedes aegypti mosquitoes. In this model, we want to answer 3 questions. 2, what is the minimum number of overtraps that should be spread in a region to eliminate or minimize the amount of mosquitoes? What is the best spatial distribution of these traps? How often should the traps be placed in the environment? So our agents in the model were the Aedes aegypti mosquitoes, and here we don't have humans. The aquatic stage of mosquito represented in a single class 2, and the overtraps we consider as agents that don't move. Again, we use the netlog environment, and in this environment we create the virtual environment where the red cells correspond to public locations, the green cells correspond to green areas in the city or in the neighborhood, and the gray cells correspond to residential areas. And here, the black points correspond to overtraps, presence of overtraps. And the white points correspond to Aedes aegypti mosquitoes. And the blue points correspond to the eggs of the mosquitoes. So I will show you a movie of one simulation. As you can see, in this simulation we have many overtraps, but a big focus here with eggs and mosquitoes. So probably here we don't have the sufficient amount of overtraps. So more models considerations. The Aedes aegypti female requires copulation in adulthood. It's the rules of the model. It deposited 1,500 eggs through its life. The maturation time after fertilization lasts on average 5 days. The unfertilized female will be fertilized when there is at least one male in the 1.5 cell radius. And the mosquito can move 1 cell per day in a random direction. And the initial condition, each mosquito has a 50% of chance of being male or female. If it is female, there is a 50% of chance of being fertilized in the initial condition. And in this case, its maturation day corresponds to a random number between 1 and 5. The eggs deposited in the overtraps are killed, all eggs. And for the simulation, we considered 10,000 mosquitoes, but we consider a maximum number of mosquitoes in the environment, 2,000 mosquitoes. The daily number of births per female was 175, and the mortality rate of adult mosquitoes was 70%, and the mortality rate of non-adult mosquitoes was 34%. oviposition site occur near the location where female is. And the simulations, we made, performed one simulation, some simulations considering no overtraps, and simulation considering 4,000 overtraps, and other considering 6,000 overtraps in the environment. And with relation to distribution, we consider a uniformly distribution in public location, residential location, and green areas. And we consider a non-uniformly distribution related to public location. We put 60% of the overtraps in public locations and 20% of the overtraps in residential locations, and 20% of the overtraps in green areas. And related to the frequency, we considered only two. We have to perform more simulations. We considered simulations considering all the time with overtrap, without removal of overtraps, and with insertion and removal, and needed 30 days of overtraps. So it was the first experiments. We made 40 replicates. 40 replicates were generated for each combination. We wanted to perform more, but the patterns were the same. We observed the patterns were the same, and graphical. Okay. And the results. Without overtraps insertion, we can see we selected this sometimes that was interesting to see the model. So in the beginning, in the 13th day, we have mosquitoes, but we can see the amount is bigger then. And we have a large amount of mosquitoes in 106 days, for example. But when we consider the insertion of 4,000 overtraps distributed uniformly and permanently in the environment, we can see that the number here, using overtraps, and we have some foci here, some outbreaks of mosquitoes and eggs here. And we observed in simulation the semi-qualitative behavior with the other distribution of 60% of overtraps in public locations, 20% in residential location, 20% in green areas. It was the same qualitative behavior. So considering overtraps, and it was not sufficient to minimize the mosquitoes' proliferation. And considering 6,000 overtraps distributed uniformly, but with insertion and removal periodically, in each 30 days. So we selected some different days, but these are the scenarios with overtraps. And these are the scenarios in that moments that there aren't overtraps. And in that moments, we have a mosquitoes proliferation. And the same qualitative pattern was observed for the set of simulations that consider periodic insertion and the removal of overtraps regardless of the number of traps and the spatial distribution. So this frequency is not good. And consider 6,000 overtraps. We can see that after a long time, more than 1 year in this model, in this simulation, but we have the eradication of the mosquito. In reality, it's not possible, but in the model, it was possible, okay? And its distribution, the overtraps distributed uniformly and permanently, but the semi-qualitative pattern was observed for the simulation considering this other distribution in the environment. So, conclusion, with regard to the objectives of the first experiment, we proposed the proposed frequency of insertion removal of traps was important to control the mosquito, but a smaller frequency needed to be tested. And different tested distribution of traps did not result in vector control, but it's possible to conclude that it's important that they are spread in all regions, avoiding breeding center, as we see in the model. And the number of traps were a determinant for mosquito eradication. We believe that there is a minimum number of good number of traps to put in the environment. So, thank you for the attention.